All right. Good morning, everyone. Uh, let's start. Do you have any questions before we start? Okay. Actually, just out of curiosity, how many more lectures do we have, including this one? 3, right? Or 2? Do you know? Yeah. Good morning, Sherry. Okay. Awesome. So, yep, I will try to see if I can cover as many topics, as I can uh, by the end of the semester. I mean, I want to make sure I go, I spend more time covering a topic rather than covering too many topics. But it's good that you see, enough of things before the semester ends. All right, so I'll keep that in mind. So today's lecture, first, let us start with the American option. So that will be, let me see here, that will be chapter 8 in the notes. All right, so far, right, let's just review what we have been doing. So, like if you take a more macro point of view about option pricing or what we've been doing in math finance, you see that, right, in terms of um, option pricing, there are several aspects, right, to this business. The first aspect is modeling. What kind of model do we use for the underlying? So this is model for the underlying, right? And I mean, so far we have 3 possible options, including, right, the binomial discrete time option that we don't talk about in this class, binomial model, right, by the binomial discrete time. B is the Black-Scholes model, and C is the jump. So try to see, for example, how each of this model influence the way you would work on the pricing in terms of computation, right? In terms of the theory, in terms of computation, and in terms of like, what you can do with the model in terms of like relating the Greeks, for example. So, but the first step, right, is we start out with the model. And then second, right, you look at, well, what kind of option it is, right? Type of option. And so far, right, there are, I guess, roughly 2 types. The first one is what we call European type or vanilla kind of, right? So basically what it means is there's not much to it. The whole point is here, there is an expiration time and you get the payoff that depends on, how the stock behaves at that terminal time. And for this vanilla type of option, right, you would have V0 to be expectation, right, like this, or I guess let's just do VT in general. t minus t, right? All right. And so this, right, is what we call pricing by expectation. And for each of this model, right, the first question you would have is, can I compute this, right? Can I compute this? How, and when you ask, can I compute this? Well, there are many ways, right? There are possibly at least two meanings to this. The first one is just by formula, right? By formula, is it possible? And with vanilla type of option, usually you expect that by formula, it should be easy, right? Especially with the Black-Scholes model, you have the Black-Scholes formula, for example. With the binomial model, you also have a formula, right? But probably at that time, I'm not sure you write down a formula or not, but you see that there should be also a formula for binomial model and the jump model, for example. So the type of the option, right? Because it's kind of easy, the formula you can write down. We also mentioned, right, another approach called the Monte Carlo, which actually doesn't really care about what type of option you have. The method is always the same. Basically, you see, Monte Carlo has more to do with what model you use. In other words, right, if you use different models, you have to think of how to simulate, right, the path, the behavior of that model. But once you have the behavior, right, the path of those models, you just plug into the option, and the expectation, right, is just the average over the whole, like, kind of different paths. But Monte Carlo simulation suffers, right? So from a different kind, right? So maybe let me say this, right? So the formula is easy by option type. And the formula actually got influenced, right, by the model type. So the formula can be hard, maybe difficult, right? So let me say this. Let me cut this. So the formula can be, so it can be easy by option type, but maybe hard by model type. So in other words, right, if I make a model more complicated, for example, right, the list goes on here, okay? I mean, there is a class of model called the Heston model that is quite popular in practice, but we unfortunately don't have time to discuss in this class. Heston basically is the so-called stochastic volatility model. It addresses the issue of the sigma being constant in the Black-Scholes model, right? Because with the volatility smile, you see that the volatility is not a constant at all. So modeling the stochastic, the volatility being a stochastic, right, process that helps capturing that phenomenon. But of course, when you make that volatility stochastic, the formula, right, that you can try to compute the value of the option becomes more complicated. And actually, I think Heston model does not have closed form formula for option price, even with vanilla option. But so, right, the explicit formula here, the closed form formula, sort of is dependent on the model. On the other hand, the Monte Carlo simulation, you will see, right, and I hope with your experience that it really is about how you simulate the model of the path. So kind of depends on the model. But does not care about option type. Okay, but of course, multi-color simulation suffers from a different kind of issue. It has issue with with accuracy, right? But it has accuracy issue. In other words, I mean, when we say it does not care about option type, I guess what we mean is it doesn't care about the how you implement it. I mean, at least naively. But of course, the option type will influence how accurate, right, the Monte Carlo is. And actually, even with vanilla option, you see that Monte Carlo simulation may not be accurate enough for us to even do the Greeks, right? But the implemented, like again, but the implementation, right? Monte Carlo has the nice aspect that if you want to implement any option type, all it cares about is how you simulate the model, right? But so the vanilla type is kind of like the easy playing ground for us to test out our model. The more serious, right, type is the exotic path-dependent options. And this is where we expand our concept of how, right, how we think about this object right here. I guess here we don't, oh, I'm sorry, right? There's one more object called maybe, right, the relations, right, between the Greeks. And so, right, here we kind of talk about, right, relation about the Greeks is basically a PDE, because PDE is the differential equation that relates all the partials, right, relate all the Greeks. But of course, again, right, if you have a discrete time model, then there's no PDE. So actually, this only applies to continuous time model. But with continuous time model, right, with different models, you can see that we have different PDEs. So this PDE is influenced, right, by what model you use. And if you use like a jump model, right, like the midterm, then you pick up extra terms that does not appear from the Black-Scholes. And if you use a Heston model, for example, then again, right, your PDE will look different. So this, right, well, I guess also depends on model, right? But on the other hand, the idea, right, of the PDE, so actually maybe I want to expand this, right? The idea of the PDE actually is what? The idea of the PDE, at least for the vanilla option, right? So main idea for the PDE is that, first of all, option, right, price is only a function of T and ST. Okay. If you know the stock and you know the time, you know the option price. Why? Because it's a vanilla option. Okay. There's no path dependent issue. There's no complicated way that you define the option. Therefore, right, the abstractly, whatever model it is, okay, the option price is a function only of time and the stock price itself. And, right, the other idea is that the discounted option price is a martingale. Which, right, why is this important? Because this allows you to conclude that whatever the DT term, right, is going to be zero. Right. So because it's a martingale, when you do Ito's formula here, right, whatever the DT term is zero, which allows you to deduce the PD. All right. So again, right, why is this important? Because you see exactly this doesn't quite hold for all the types of option. For example, right, with the exotic option, that roughly, yes, we still have something like that, but we have to modify this a little bit, right? And this relation also gets changed. So, but so the martingale principle, right, is important when we analyze like European option, for example. when it comes to exotic path-dependent options, right, what changed? So first of all, right, fee, right, the payoff now is a function of the whole path. First of all. So therefore, right, when we do this, so the formula is still the same. I mean, in the abstract, for example, let's say this. But, right, several things happen. This is the whole history of the stock price, right, from time zero to time big T. So we cannot simply just separate out the value s little t and say that is only a function of t and s little t, right? So the whole history here requires us to have much more than just, right, that little st. And in fact, right, we see that the main principle is it depends on one extra variable. This extra variable somehow captures, right, the history from time 0 to time little t, right, depending on what type of option it is. So that's the first thing. But also because of the whole path nature, right, the question of can I compute this becomes much more complicated, right? And so here, right, I guess I didn't write it down, but the expectations most of the time, yes, right? I guess possibly yes. I'll be very surprised if for vanilla option you cannot compute it for any reason. Okay, I cannot think of even for a very strange function phi. Well, abstractly you just plug in, right, whatever phi it is. But here, right, can I compute it? And so if you ask for a formula, then the answer is possibly no, right? It really depends on whether I can compute the distribution of this guy right here. Okay. So you remember that actually is where we spend like quite a bit of our time on for the running max, right? For the running max, it's possible. So if yt, right, is the running max, then this is yes, right, by the reflection principle. And if it's going to be the integral, then it's no. And let me put a question mark here, right? I mean, because actually when you say no, it's a little bit strange because maybe no, because you're not smart enough, right? Maybe someone else who comes along who has some strange trick, right? Like the reflection principle may be able to do this, who knows, right? But at least the current state of knowledge is that there doesn't seem to be a clever way to do so, okay? Which is kind of strange because in some way this object is a nicer one to look at than this one, right? But you know, like these are just two possible ways to compute, to form the path, right? In general, it just says that it's a function of path. Who knows if there's other crazy ways, right, to combine the path. So the answer probably is, again, right, possibly no in general, right? The whole path nature of the stock makes it much more complicated. And Monte Carlo, right, probably shines here a little bit in the sense that, again, right, it doesn't care about what type of option you have. It just asks, well, you simulate the whole path anyway, right? Let's just plug that path into the function, do it so many times, and then average it out, right? So Monte Carlo, in terms of approach, is still the same. But of course, right, that's not the whole picture, right? The accuracy gets worse. And why is that? That's because you have to simulate many more things, right? And so to capture, right, to make it converge, you must have more samples. And of course, even with our current state of computers, right, 1,000,000 simulations is not that fast to do it. So like again, right, this opens up the question of how do you speed up Monte Carlo simulation, which is not the point of the class. But like, so I guess the point is, one thing you want to see is when the formula or when the simulation gets more complex, right, then the analytic approach has its place, right, and one should think about it. But the computational approach starts to take over. In other words, right, I mean, this is why I'm not sure you hear, like in practice, the banks or companies like to do, I don't know, like historical simulation, that kind of thing. Well, okay, his historical simulation is simulation by historical data, right? What we're doing is Monte Carlo simulation, which is like possibly future simulation. We simulate, right, random scenarios in the future. But I guess the word simulation is still the same here. In other words, right, you just use whatever path you have to test out what kind of scenarios you have and average out over those scenarios to get like an approximate idea of what's going to happen. So in other words, right, you see, basically to handle, to have an idea of how a more complicated product, right, like starting with exotic option, then the idea of simulation starts to kind of be more and more relevant, and the analytical approach become, I would say, more tedious and sometimes, right, not possible. But still, we still have to kind of keep the structure in mind to not, right, make any kind of weird error when we discuss this kind of, basic object. And the PDE, right, the PDE approach also gets more complicated, because for the PDE, right, first of all, we have to keep in mind that potentially, right, our function depends on the option price depends on 3 variables. Okay, so that gives us many questions. For example, first of all, the domain issue. How does S and Y get related? Okay, any relation at all? But the moment you open up the domain question, you will have the boundary condition question. What happens when you push out at the boundary of the domain? Okay. Finally, right, even the martingale question. Let me say martingale characterization. All right. So we've not emphasized so much in the third part here, right? I kind of keep asking about these 2 parts, but this guy also is there in this way, right? Let me just say this. The principle, right, is still something like this: eta minus RT, VT is a martingale, roughly. That's still the same, right? I mean, if you look back on how we were doing, right, I mean, our PDEs with the exotic option, this is more or less what we used, except if you pay attention to the barrier option, okay, there's a subtlety there. When we say the barrier option, right, the discounted option price is a martingale, we say that up to a stopping time. Okay, up to a stopping time. So in other words, this martingale condition, right, before, when you have the vanilla option, it's gonna always be a martingale from time 0 to time big T, okay? from time 0 to time big T. So from the start to the end is always the discounted option price, always a martingale. But here, right, it may be a martingale only up to some time, right? So that's, first of all, that weird thing, okay? So with the barrier option, it's a martingale up to the first time the stock hits the barrier. The second, right, issue is how do we understand DYT, okay? Okay, you have a new process here that the option price depends on. When you do the PDE, you must understand how the Y, right, evolves with time, because that will feed directly into the Ito's formula, okay? And again, I kind of not emphasize too much on this, but you see, understanding DYT for the max is very different from for understanding the DYT for the integral, right? So that makes the PDE for the look back option looks very different from the PDE for the Asian option. Again, that has to do with the DYT, okay? So all these issues, you see, how to say this, right, comes from the structure, right, of the option, for example. And I just laid out like this as a typical, I don't know, program that one would go through, right, in the steps of, I would say, approach any kind of problem, even not in option pricing. First, you have to ask what model do you use, right? And then you ask, okay, what kind of formulas, what kind of math do I use to get out the relation into what I want? And then you ask, can I compute that formula, right? That I just came up with. And each of these questions, right, requires you to approach with different, roughly, areas of math and areas of knowledge even, right? And let's not even get to the area of statistics, where you need to calibrate, right, the parameters of this model, which we don't discuss, right? That's time series or something like that, regression. And then the area of data, right, where you, again, you know, kind of collect data and then try to use those data to calibrate these models, right? And there's the whole area of finance that we don't even discuss there too. So many things, right, to keep in mind. But hopefully, right, this kind of capture all the main points and all the main ideas that we've been doing so far, right, up to now. And it will be good if you keep these points in mind for comparison, right, with what we'll be doing in the future, to see the difference, right, the similarities and the differences as we continue. Any question here? All right. So one reason why I mentioned this, okay, is because when we talk about American option, right, it is yet another approach, another type, right? So this is going to be, so the model, right, let's talk about the model. The model will be the Black-Scholes model, right? That's a standard model that we always use. But the option type, right, will be very different. It's not exotic, but it's not vanilla either, right? Because it relies on a different object, right? So it relies on the so-called, so it has two components, right? So of course it has the expiration time. It has a payoff function, and let's call it G, okay, G of X. But then there's another one called the class of stopping times, right? So we look at the class of stopping times. Taking values from 0 to big T, okay? So these three objects. With these three objects, then basically, right, with the American option, I guess you know already, there's no such thing as V big T rather, right? I mean, there will be some V little t, but we have to be very careful to formulate it. Basically, right, the option holder has access to all these three options, right? And usually, right, so their point of view is this. Maybe, let me just say, maybe actually here 0 to t is not even correct. Let's say little t to big T, for example. So here we talk about their point of view at time little t, right? Looking forward. What they have available to them is all the stopping times from time little t to time big T. And what that means, right, is their choice. What they can choose, right, is going to be to receive the payoff G of S tau at that stopping time. Okay. So in other words, right, in English, an American option holder, right, the option holder can choose a time, right, between t to big T to receive an amount where G, right, is our payoff function. Okay, maybe let me change that to phi. So this is from the point of view at time little t, okay, at time little t. So what is the big deal here? The big deal here is two things, right? First of all, there's no fixed time that the person has to exercise, right? Has to exercise the option and receive like a payoff. So basically, even, right, I mean, so there are two things. That the time that they choose, not, oh, okay. I think you use a term there that I'm aware of, but I have to ask what you mean exactly. I think so, but the intrinsic value doesn't have to be only specific to the binomial model. I think maybe that's why you heard Professor Larson mention it, but the intrinsic value can be defined, I think, for any model, right? I mean, it's a financial term, really. So I think, yeah, it is not specific to the binomial model. But yes, I think it's something, probably I have to ask you what you mean by intrinsic value. We'll talk about it. But basically, what it means, right, is the option holder at any time will have at least, right? So what it means, let me say this. After we discuss this a little bit, all it means, at least one implication is this. Okay. What it means is that the option value is always at least that value. Why? Because the option holder always has the option to just exercise right away and receive this much value. So if by that you mean intrinsically he has access to that much value always, then yes, that's called intrinsic value, right? But all that it means is that, you know, at any time, right, the person can choose to exercise. So he's guaranteed access to this value at any time that he wants. Is that okay? And again, the consequence is this. So yeah, but I guess to continue on that question, right? Basically, this object right here, this object right here, right, means that the person can choose any time between little t and big T to receive the value. So the point I want to make, which is probably not a big deal, but this time right here, right, potentially is a stopping time. So in other words, it can be a random time. Okay. For example, a person, right? So tau, right, can be random. In other words, the person can say, I will exercise the first time that the stock price goes above some level L. Okay, so this is not a barrier option, but suppose that so in terms of picture, right? Here's T, here's ST, right? Here's L, right? The person who has this American option will say, you know what? I don't know when I want to exercise my stock, but let's say that at the first time that the stock hits that level that I want, I'll exercise. All right. But you see, right, this is a random time because this is a possible path, and here's the time he will exercise it. A different path may be like this, where this is the time he exercises it. Another path may be something like this, in which case, right, he, quote, never exercises, but actually what it means is he will exercise at time big T. Is that okay? So on path 1, right, this is tau 1. On path 2, right, so this is path 1. On path 2, tau 2 is equal to T. On path 3, for example, this is tau 3. I mean, these are all really 3 different instances of tau, of this value tau, right? But I guess this is probably the first time we see that the random time, right, has an effect on how the option price will get paid, how the option will get paid, right? Before the time that the person get paid is always a deterministic time, right? Time big T. Here is the first time that the time you get paid can be a random time. Is that okay? So the holder, right, task will choose, if possible, an optimal time, tau star, to exercise and maximize the expected payoff. Okay, phi tau star. Like this. Okay. So in other words, right, for each choice of time, from time little t to time big T, right, this is the person's expected payoff from the point of view of time little t. The person, because he can choose any time that he wants, he will want to maximize this. So in other words, VT will be the max or the sup over all tau from time little t to time big T of the expected payoff. Sorry, not tau star, as tau star. Okay, and this will be our definition of American option. Okay. Any question on this before we continue to discuss what this object is? So first, right, let's kind of go back to the easy type of payoff option that we usually look at. So the two most, right, you know, I don't know, popular choices of payoff, right, function is when phi of x is x minus k plus, and this will be the American call. And when phi of x to be k minus x plus, this will be the American put. Okay. And so you see, I hope that you get the intuition. At least you should try to see what the problem is about. So for example, at time 0, okay, to time big T, here's S0, right? And the stock can go wherever it wants like this. And suppose here's K, all right? K is somewhere here. And so the person, right, at time 0, for example, can choose any time from here to here, right, to exercise. So for example, if the person chooses right here, then the payoff, right, will be this much. But the person can also choose to exercise here, which means the payoff is going to be this much. So this is tau 1. I don't know, right? Maybe here, tau 2 like this, and here, right? The payoff will be this much. Okay. So let's ask you this. For example, see if you can kind of get the intuition here. Suppose that you are an American holder, right? Suppose you have an American option. Right, call option. With, right, let's say again, strike K and expiration T, right? How would you choose a time to exercise this option? Right, I mean, suppose you have an American option on Google stock with 3 months to expiration from today. How would you choose the time? How would you choose? So you can exercise anytime from now to into 3 months. How would you do it? What would a possibility that comes into your mind? Any idea? I mean, you don't have to come up with an optimal choice, just maybe some sensible ideas here. Anything?
Will you possibly choose the tau that first might be equal to k by any chance, or
Yeah, so I think
k?
Kashif and Don agree on that. Monte Carlo simulation is probably a vague answer, meet, right? I actually I like that. We will get back to that too. I think what you're thinking is something else, right? But first of all, right, let's just to be concrete, let's say S0 equals to 100. Let's say K equals to 100. All right. And so let's look at possibilities, right? This is Don and Kashif both kind of come up with this. But let me say this. Suppose that this is what you choose, then when you exercise. If you really go with this, what is tau here? I would argue that maybe you don't realize it, but maybe essentially you're saying tau equal to 0. Do you agree? Because, right, for example, yeah, no, I like the idea meet, but we'll discuss that, right? But yeah, this is not that simple. We'll discuss that. But in fact, I will discuss what you're discussing, what you're mentioning right now, right? But right now, I want even a simpler one, right? Like what Don and Kashif was discussing, so we can just have an intuition. So what I'm trying to say, right, is if this is the case, you see, now of course, I think what you have in mind is something like this, right? But like for example, let me just make it easy, right? Let's say 95. Yeah, okay, I get it. But you say the first time, right? So as long as the stock move 1 cent above that, then you will say, right, that they're above. So I get it, but because of the if, right? But let's look at this. Then do you agree that tau equal to 0? If S is 100 and K goes to 95, then tau equal to 0. Do you agree? Okay, let me ask you this.
I guess that would make sense.
Is this optimal?
It's not optimal, isn't it?
Right, but I think, right, at least you would suspect, maybe not, right? Because maybe the stock can go better, right? I mean, for example, so basically, right, what you're saying is that the time, any time, right? So basically, tau equal to 0 is a possibility. In other words, you don't care. You just exercise right away as long as you make money, right? As long as you make money, you exercise right away. But maybe, right, at least the gut feeling is it's not too optimal. Okay. Maybe a better one could be something like this. First time that S is bigger than L, where L is to be decided. I mean, you have to decide right now, right? But L is chosen, right? L is, let me say, L is you know, suitably chosen. Let me say this. For example, right? Let's look at this scenario. Is it sensible for me to say first time S bigger than, I don't know, 105? Hard to say, right? But I hope at least you see what I'm doing here. What am I saying, right? I'm improving on your suggestion. In other words, I say that, right? Maybe I won't exercise right away, but if the strike is 95, I won't be too greedy. Anytime I can make 10 bucks, right? I will do it. By the way, right, this bigger than doesn't mean that you will go above, right, 105. It really means that the time, by the time you hit 105, you will exercise and you'll gain 10 bucks. Is it okay? Now, what I want you to get an intuition of is simply this. What is the difference between this and someone who is more greedy and someone who is less greedy? Let's say, what's the difference between these three choices? And is it possible to say which one's more optimal, which one's less optimal?
I don't think we can say which one is more optimal because, like, if we're more greedy, it might not happen, and then it might end up worse.
Yes, Cherry, I think, right, actually what I want you to see, right, is this, that it's hard to say, I agree with you, that which one's more optimal. But if you are more greedy, the one possibility though you see is this may not happen, right? Okay. So by the way, right, I hope you understand, if the stock never goes above 120 before time big T, then what is our exercise time? What is tau in this case, if it never happens before?
It would not be existent. Like tau not be existent.
Not quite. Okay. Let me say this, right? Suppose, right? Okay. Let's take a hypothetical scenario. Let's say again, right? This is 100 and K is 95, right? And let's say that the stock. So let's say that really your decision is this, but the stock does whatever it does, and it ends up in 118, right? So if you're saying it never happens, or if T is infinity, that means you throw away the stock. You throw away the option. Would you throw away the option in this scenario?
Yes, yeah.
No, I don't agree. Why is it worthless? Remember, K is 95. Yeah, on the final day, don't you receive this much, which is, I don't know, 23 bucks, right? So, oh, no. Do you see, Kashif? Make the distinction between, right? This is where, that's why I want to make sure these are concrete. K, right? K is the strike, but L is that level where you want the stock to reach before you exercise. So, right, this is exactly where you and Don, I'm not sure about Don, but you seem to mix these two together. In other words, right, you want the strike to be the first time too, but I want to separate them, right? They don't have to be the same.
But Prof,
Yeah.
Isn't it even in this case, the very first time we can have S equal to 120 and it would be essentially tau equal to 0?
So the first time that you say the first time that a stock is bigger than 120 is time 0. Is that what you're asking?
Yeah.
No, right? Because the stock start at 100. So you are correct to say that the first time that the stock is bigger than 120 is infinity. Right? It never happens. So you are correct to say that tau is infinity. But on the other hand, I would say that because of that, the exercise time should be big T, because you should not throw away the stock. Or you should not throw away the option. That's all I'm trying to say. It's not worthless. It's still worth something. So in other words, even if you set a very ambitious criterion that never happens, what all that means is, so basically all I want to say is this: infinity means T, if that is a sensible way to say it in this setup. Because right, as long as you have some kind of payoff, then why not exercise? Does that make sense or no?
Yeah, it makes sense. I mean, I was confused with what could be the value for L. So in this case, L would always be greater than S naught.
See, now, how to say this, right? It should be. I mean, if with a call option, right? And there are many things here, right? So first of all, I'm just running through the thought experiment. So there's no criterion on L to begin with. But if you look at this as a call option, right? Then if you start out with 100 and at 95, and you say you want to wait, it doesn't make sense for you to wait for the stock to go down, right? Because it's a call option. You only wait for the stock to go up. Does that make sense? Because it's a call option, right? You want the stock to go higher. If it's a put option, then yes, you will want for the stock to go down. Does that make sense?
Yeah.
So yeah, that's the only thing, right? So L here is bigger than S0 because it's a, otherwise you would already exercise at time 0, right? So yeah, all I want to kind of mention, and so that you see is, right, even if whatever criterion you choose does not happen, you still possibly want to exercise at time t. So infinity here, right, just is equal to t. Okay. So Don, I saw you say ST is already greater than K. It may not, right? At some point it may.
Yeah, I mean, I'm just saying that like in this scenario, so I guess it's not entirely worthless, but the tau would probably
right. But let's say this, right? Let's say that another scenario. So what I want to say is this, right? Suppose there's another scenario that the stock is doing very terribly. That, suppose it ends up at 90. Okay. I would argue that in this case, it doesn't hurt for me to set tau equal to t. Do you see why? Because if I just exercise here, what do I collect? With k equals 95. 0. But that's the same thing as I never exercised, right? So basically, to make everything easy, right? As long as the payoff function is always positive, which would call it put is always the case, you always at least exercise at time big T. You never throw away the option. It's just to make things easy. But of course, I mean, in real life, if you get it's worthless, why bother, right? Is that okay? So you always at least exercise at time big T. That's the only thing I want to make it easy. Is that okay? All right. So right, I think that's enough thought experiment. But basically, I guess there are three possibilities here, so we can see, right? So 3 big possibilities maybe, and among too many things, tau equal to 0. That means you exercise right away. That's possible. Tau equals to t. That means you never exercise early. And some compromise, right? Tau in between. Right? And in between in quote, because it really depends on how you, right, set this level, for example, right? Okay. So what's your guess? Right? What's your guess? Which of these three will be the right answer for the American call option?
I guess it depends on like what the value is for like S capital T.
What do you mean by that, Don?
Um,
So remember, right, you have to be realistic here. We don't know S capital T, right? I mean,
oh, we don't.
yeah,
Okay, so
I guess what Meet was saying about simulation, right? So I'm simulating in my mind, right? I'm not doing Monte Carlo, but I'm simulating in my mind these values. So see what would happen. But clearly, right, here is where I am. I do not know this at all, right? So here I am pondering these three possibilities. Very good, Kashif. Yeah, Sherry.
Oh, I think the second one.
Ah, also very good, right? What Kashif was suggesting, I think, is an excellent choice in general. You know, these are two extreme, right? Boundaries. You suspect it doesn't happen, but right, the optimal one should be sometime in between. But Sherry is also right in the sense that somehow, surprisingly, with the call, this is the right. So let me say 2, right? And 3. So surprisingly, right, 2 is the answer for the call. And we have to say this, right? As long as stock doesn't pay dividends, which may happen in practice. And 3 is the answer for the put. Again, there's some condition here. As long as R positive. And I would say 3 possibly is the answer in general. Okay, 3 possibly is the answer in general. So 2 is very strange, right? I would say intuitively 3 is the answer, but somehow 2 is the answer for the call. Okay. So, right. So let's see here. Let's try to address this. I think maybe at one point I did try to answer this. I did show you this maybe first day of class, but let's see if anyone remembers, right? So why 2 for American call?
Oh, my guess is that usually when we compute like these prices, we or the payoff, we discount it. So then I'm thinking if we move it to the latest time point, like its expected value would increase, I think.
Great guess, and I think you base it on the math, but let's say this, right? Someone who kind of like would want to push the question will ask you, wait a minute, the longer you wait, isn't it true that the more you have to discount? So why is it that it has higher expectation?
Wait, sorry. So the longer we push it, I think it gives it more time to grow. Or I don't know.
Why more time to grow, right? The stock can be up and down. If the stock always grows, then we all will get rich already.
I think because of the like, I don't know, maybe because we use risk neutral probabilities, that it's just like it still has.
That may tick some people off because they may not know what risk neutral is. They don't want to go anywhere near it, right? But you're right. I'm not saying you're wrong, but to convince someone, right, especially on an interview, this is really not enough. I would actually agree with you. That's sort of the reason. But you see, I'm just trying to see if you want to see that with an interviewer, it's not enough to say some fact. You want to convince them, whatever that means,
Yeah.
So what do you mean by infinite upside, right? How do we see that? You're kind of, I think, trying to say something similar to what Sherry said, right? But how do we know that? So maybe, right, let's first go back to, or let's try. It's always kind of good to keep the American guy with his cousin in mind, which is a European, right? Okay, I see what you mean. But what you say actually doesn't quite work, because for the put, the stock can still crash all the way to zero, right? In which case you also get max profit. Does that make sense? Yeah, it's capped at s equal to zero, but that doesn't explain why I don't want to wait until all the way into time big T for the put. Does that make sense? Because I mean, who's to say that the stock will not go down further? Because we're talking about a time, right? The waiting time. I see what you mean about the cap profit, but I mean, I don't see how that's related to waiting, because for example, all I'm saying is this, right? That sure, what you're trying to say, right, is this is K. If this is a put, this is all I can collect, right? If it's a call, the sky's the limit. I agree. But like from the point of view of a stock, right? It's supposed like this. All right. I mean, just because, right, my profit is capped below, that I don't see how that will convince me that, okay, I should not wait until all the time at the end. You see what I'm trying to say? Because I mean, my goal is to max profit. It's not to infinite profit, right? And so at least from this point of view, it is unclear, right? And in reality, right, we see that stock doesn't explode sky high too many times. Stocks sometimes also crash, right, all the way. So yeah, I'm not sure the upper bound explains it though, right? The unboundedness above explains it. Do you agree? I mean, I think I have this to say, right? That what you're thinking, actually, funny enough, you are anticipating what we're saying. Like if we have something called perpetual option. Okay, I think that's what you're saying. And actually, you will see that you're right here, actually. Perpetual American option means t equals to infinity. Okay, so, like in this kind of thing, right, we say that you have to choose a time between 0 and big T, right? There is, I don't know if it happens in real life. I think it can happen. But basically here, there's no horizon where you need to exercise by. You can choose any time until now, from now until the end of the universe, okay, to exercise. Does it make sense? Then if this is the perpetual option, then what you say meet is exactly correct, because I can wait for the stock to get higher and higher, right? To get as much profit as I want, while with the put, right? I mean, it can only get so much, but that's to in provision that I have all the time in the world to wait. Yes, but if I can only wait from now until 3 months, then the story is different. Do you agree? Because it's definitely very unrealistic to say that a stock will go sky high from now to 3 months, right? There's only some kind of range that it sensibly going up or down, and then within that range, right? I mean, if you want to talk statistics, for example, right, 2 sigma, right, is something that we go by. And suppose that 2 sigma is going to be something like, let's say 105 to 95 is 2 sigma for this stock. Then the possibility of it crashing or the possibility of it going sky high is equally impossible. Does it make sense? So, right, your argument works here, but with a finite time, it's a different story. Okay. All right. So, but these are very good thoughts, by the way. Actually, they all have some ideas there. But let's go back to, right, what I want to ask about American versus its European cousins, right? Right. So I hope that is clear to everyone that the American is always no worse than its Euro cousin, right? Because you can always, right, forget that you have an American option, and then just, right, exactly here, the convention that we always exercise at time big T says that, right, at least you always exercise at the end. And so the American, right, will turn to European option. And so, right, if you have an American option, its value will never be worse than the European option. So what we're saying, right, if 2 is always the answer for the American call option, do you see what you're saying? That what we're saying? That we say that the American call is always equal to the value of the European call. Right? That's all we're saying. If we say that 2 is true. Okay. So I guess I'm saying this to kind of guide you on thinking path, because again, I guess going back to what Sherry was trying to explain, saying something like this would be very convincing to the interviewer, because well, of course, right, and then they will be pleased to see that you're saying something like this. In other words, right, this is a logical statement that anyone would agree, right? So, but then the next question, of course, is why is this true? Why is the American call always equal to European call? So, right, you introduced the European option as a thinking tool. But then how do you use this thinking tool to explain the detail of that? Well, so the European call, right? So actually, I think with the binomial model, right, there's this convenient idea of this, right? So suppose at time t, right, at time t, suppose you have the American option, right? What are two simple decisions that you can think of when you have American option at time little t? I guess, right, the decision can be complicated, but if you want to really simplify it, there are only two decisions to make, either to hold or to exercise. So maybe to continue, right? Or to exercise, right? And what will influence your decision here? Whether you want to continue or you want to exercise?
It depends on what K or L is, or SO.
It depends on what K is, right? I think that's what you're saying.
Oh, okay. Yeah.
So what it means is this, right? If you exercise at time t, how much are you collecting? You're collecting ST minus K plus.
Right.
Okay. But how do you know that it's not wise to continue? Sorry, it's not wise to exercise, because if you exercise, right, you will get this much. But how do you know that is? How do you know your continuation value? Or how would you estimate your continuation value? Let me give you a clue, right? It's no, Sherry, you're still thinking of expectation. Here, right, it's really more primitive than that, but it is also a good thinking tool. If we continue, the answer is we don't really know what the continuation value is, but we know that it's at least V euro call. Do you see this? Because, right, V euro call means you continue all.
Yeah, that's true. Yeah, I see it.
So at least I should get that much, right? So, but if, right, so now you see what is the key comparison. The key comparison is between V euro call and the exercise value. If somehow this is always bigger, right, which is a question, I don't know that, but right, if this is true, then do I ever exercise? No. All right, no. And I believe, right, Meet, I think, was the one who asked about intrinsic value at the beginning. Again, this is where I usually see, this is the context where I see intrinsic value get brought up in discussion. And if I'm not mistaken, all right, I believe somehow this is referred to as intrinsic value for the American option. I forgot, right? I apologize. I don't know this precisely. The explanation is this. Basically, intrinsically, you always have this much or more or something like that. Okay. So let me look back, but and see if I can dig up some reference to see what intrinsic value really means. But you know, basically, just for your reference, I mean, I do know that this is exactly at this point where the concept of intrinsic value got brought up, but I forgot what quantity it gets to, it refers to exactly. Okay.
In Professor Larson's class, I think that's why it was brought up. I think he just referred to the intrinsic value as the value once you exercise it at that time point.
Oh, so this one then?
Yeah, so that one was just the equivalent of the
I
intrinsic value
think, Sherry,
basis.
that was what I was telling Meet at some point, and that's my gut feeling. But you know, term right has exact meaning, so I don't want to say something that I don't quite know. But yeah, thank you. If you can confirm that, then I think it's this.
Yeah.
Yeah, thank you, Sherry. So anyway, I would definitely trust Casper on that one. Anyway, right? I mean, as far as I'm concerned, I don't need that concept really, right? All I'm looking at is this. If I were to continue, right, my continuation value must be at least this. If I were to exercise, this is what I get. So if my continuation value is more, strictly more than my exercise value, I would never, right, exercise early. Okay. So it's really boils down to this equation, this inequality, sorry. Does that make sense? So now then, can we establish this? How on earth is this true? Now, again, I know Sherry would say something along expectation. Don't give me expectation. This is not the point of expectation. Expectation is where we used to, you know, start to be sophisticated and you know, do all this calculation to get implied volatility, etc. Right? And you see, that's where it's used. Here is very roughly an explanation, a discussion among the financial lines. And so people would really hesitate when you drag an expectation, that kind of thing here. Right? So is there any way we can establish this? So recall, right, this good tool of put call parity. Right? So I would just abbreviate by VE, okay? VE call minus VE put. What are you talking about here, Kashif? Money market? So you're talking about like a saving account, not stock? So if you want to explain what you want to ask more details, I'll try to address that.
So I realize I'm going in the same lines as Sherry.
Oh,
Because,
you mean like in terms of expectation? Yeah.
not in terms of expectation.
In terms of discounting?
In terms of rate. So if you just invest in the money market, like fixed income kind of a thing where the rate is fixed.
I love how you like to think in that terms, but don't forget, right? That's future. Yes, in the future, right? That's time value of the money in the future. But exactly, you see, if I promise you $100 today and $100 by the end of the semester, which one do you take?
That is today.
Right. Why? Because $100 in the future gets discounted, right? So therefore, sure, your money will grow, but then if you discount it back, it's exactly whatever you're having today, isn't it? Right? So that growth in the future should not be taken into account if we are discussing action today. Or in other words, right, if you have any future stuff, to translate it back to the present, actually you have to discount it, not right increase its value. Does that make sense?
Got it.
Right. So if you have something that somehow tends to push you toward the future, that is very suspicious, meaning there's something interesting going on there, right? Because things tend to actually get drawback, right, by discounting action. That's all I'm trying to say. But of course, I'm talking nonsense. In a stock, right, there's the whole random action that can push it up or down, right? And that's what we're discussing here. Is that okay? So, right, with put call parity, right, this is this. And by the way, funny enough, maybe, right, Kashif and Sherry keeps wanting to use the R. Yes, your R will come right here. Okay, that's where the R will come. Yes, so I would say the R does play a role in here. Okay, so first of all, this is put call parity. Are we okay? This is put call parity. Okay. So going back to the whole intrinsic value business, right? This says that VE call will be ST minus K minus RT minus T plus VE put. Okay. Now, you see, I think this is interesting because somehow I keep telling you R doesn't matter. Here, it exactly at this place where R shows up. Because if R is positive, this is bigger than do you agree? Because exactly because you have discount here. So subtracting this, right, is definitely less than subtracting this. All right. Now then right, then you're done because this guy is non-negative because it's a put option, right? So when ST minus K is positive, then this is the plus. So this equation holds true, right? This is true for any ST and K. But of course, then that means, right, is bigger than ST minus K plus, right? When ST bigger than K. But of course, right, when ST is less than or equal to K, this is just 0. And this is also bigger because we know that the call option, right, value is never 0 exactly. So what that means is that this is true. So yeah, I mean, I don't know, right? The option value is always bigger. The call option, European call option is always bigger than its intrinsic value. If you know, that's the statement you're looking for, right? The European call option is always strictly greater than its intrinsic value. Are we okay here? So the remarkable fact, right, is that there is no expectation, right, involved in this explanation. But yes, R does play a role, right? The R plays a role exactly here. Because you see, what we want to be very careful is that if we have an equality here, then it's unclear. Technically speaking, it's still okay. Because if you still have this, then it's, you know, it's an indifference issue, right? If you have that the continuation value is the same, if it's equality, if it's the same as the exercise value, then you're indifferent whether you want to continue or not, right? But you know, if it's strictly greater, then it's clear that you never want to exercise early. Oh, okay.
Wait, sorry.
Yeah.
Can I
Sure.
ask about, so this last line, like I get how it makes sense within the context of the calculations,
Yeah.
but then just like logically right now, as I think about it, is it always greater than 0? Like the price of a European call?
Oh yeah, that one, absolutely, right? Because when you think about it, if you were to go to the market and you want to buy a call option on anything, do you think you will pay $0 for it? You may
Oh,
pay 1 cent or 2 cents for it. What is the argument? And actually, this is what I think what Mead, roughly speaking, what Mead say may apply. In other words, right? If you hold a call option, will you ever lose money?
no.
No, by definition. Will you have a chance to win money, however small it is? Yes, right? You will have a chance to win money. Like now, let's take something crazy. Let's suppose that, like, let's say, right, Google is now $2,000, right? Let's say you buy a call option with strike $3,000 on Google. Will you ever make money? I would say, yeah, no, you wish. But in principle, right, the probability that it goes above 3,000 is still a tiny, 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 tiny probability, right? It's non-zero. So if you factor that into like, some fraction of money, that's like a fraction of a fraction of a fraction of a cent. But whatever, right? That's silly. But the point is that, right, that being non-zero is still correct. Does that make sense, Sherry? Like, right? Because you always have that tiny chance of making money.
Oh, I see. I think I just kept translating V into payoff, but actually it's still.
No, V is not payoff, right? V is
Okay.
definitely future payoff discounted back, right? Yeah.
Oh, I see. That makes sense. Sorry. Thank
No,
you.
it's fine. It's fine. Yeah. You see, that's exactly it. Otherwise, right? V and payoff are the same, right? V is not payoff, right? V is future payoff. Okay. All right, cool. So maybe one last question before we take a break. Do you see how this argument does not work for the put? How, right? Notice, right? The call, right, is the only one that we have the answer as never exercise early. But 3, right, is the answer for the put. I mean, I'm not saying this explains it, but can we repeat the same argument for put? Well, you see, first of all, right, if you were to turn things around, then you will get VE put will be, right, K e to minus RT minus T minus ST plus V call, right? Okay. Now, what's the intrinsic value? Now that I learned that term, I so much like to use it. You see, I'm a good student. What is the intrinsic value of a put option? Well, you see, it's something like this, right? Do you agree? I mean, I know there's a plus, but exactly like Sherry asked, right? Because of this kind of argument, the put never has 0 value, right? So I don't care for that really. If this is 0, this is always positive. If it's non-positive, then this is non-negative. If it's non-zero, then that's worse, right? But yeah, does this hold? Can I get that? Why not? What hurts here, or what prevents you from doing that here?
Would it be the European call?
Note on the European call is working in your favor, right? Because this is non-negative, so it only push it further. So
okay.
Yeah, right. You see exactly the same thing here. The put here is working in your favor, right? It may not be positive, but it always at least will push you in the right direction, right? So it's not the call that's causing trouble here. What? Yeah.
Is it like that K times the exponential thing?
Absolutely. The
less
discounting
than-
is working in the wrong direction for you, right? You see, here the discounting is working in the right direction for you, but here discounting is working in the wrong direction. So no, right? Exactly this right here. But do you see when discounting will not affect you? When there's no discounting at all, when R equals to 0. Okay, so I don't know if you have done this exercise in American option for the binomial case, but if you pose a binomial model with R equal to 0, then you will see that even for put option, what case are you talking about now?
Just like in that example you're showing, like would K minus ST be like greater?
Yeah, exactly, because of this. So that's why you cannot do this, right? No, right? You see,
okay, all right, yeah.
Like exactly my point that here, this is bigger in its intrinsic value, so you don't want to exercise early, right? Here, because of the discount, sometimes it's not bigger than its intrinsic value. So you want to exercise early, right? Especially, so you can actually hear this equation shows a lot. I would say that maybe in the high interest environment, people may want to exercise early, right? And again, I think maybe with apologies to Kashif and Cherry, something you say here may be correct in the sense that, right, there's a time value of money here. There's a time value of money here, but not in the simplistic way you put it, right? But basically, the longer you wait, right, there's some kind of price you pay, okay? But the price you pay must be explicitly put in this way. So if you wait longer for the put, right, you pay higher price if the interest rate is high. So therefore, right, if the interest rate high, you may have incentive to exercise early, right, to not pay that price. But with the call, it always in your favor, so you don't care, right? Does that make sense? So I guess in the low interest environment, the put option maybe not, the American feature on the put option may not be that attractive because you would wait until the end anyway. But in the high interest environment, yes, the American feature means a lot. Is that okay? Any question? All right, so this is, I think, enough to build intuition on the American option. Let's take a 10-minute break. So let's get back at 10:30 my time. And when we come back, we're going to do the whole, mathematical, derivation of what the American option will be. Okay. All right. See you at 10:30. All right, let's continue. So I hope everyone's back. All right, so now let's go into the business of, right, the calculation, right, of the price, and how do we understand the math, right, behind the American option. So, right, first of all, let's just run through some kind of, again, thought experiment, but a little bit more specific. Let's suppose that I'm interested in V0, okay? Let's say that I want V0, right, which is the max, right, or the soup for all stopping time between 0 and t of discounted, right? Sorry, this is tau, okay? Phi of S tau, like that, okay? This is the price of the American option with payoff function phi.
I don't see your screen.
Oh,
Hi, I'm back. I don't see your screen either.
I appreciate that. I could be talking to a blank screen for all I know. All right, cool. All right. There you go. That's hopefully improved something. Not yet. Here we go. Right. So I was saying this. All right. So let me ask this. And this is actually in connection with what Meet was suggesting, right? Please describe a naive Monte Carlo approach to calculate P0. So suppose, I have nothing better to do. So on the exam, I give you this question. I say, write pseudocode to calculate V0. How would you do so? And in case you think, this question is too boring, let me ask a related question. It's similar, actually. Right. And by the way, maybe let me write one more thing, right? Suppose that there is that sweet deal, the optimal stopping time. Then this will be this. Are we okay? So this soup right here, right, it belongs to this. So in other words, there are two things. The top is every stopping time I can think of. I do this and I take the max, right? Just think of this as the max. Or if I know whatever that mysterious formula is, for example, with a car is easy, it's big T. But in general, right, whatever that is, I will find it and I take expectation, right? So it's up, but first of all, do you agree that these two are equal, right? One with the soup, one without, because here I only plug in whatever that makes it max, all right? So I hope you see that these are equal. If you have any question on this, let me know. But take either formulation, whatever you want. Can you describe to me how you would compute either? All right, and this actually goes all the way to what Meet was describing. But think carefully, right? And I would say maybe it's too long, and verbally, speak to them, the microphone, if you will. Tell me how you would do this. I'll help you, right? First is simulate a path of S. This is easy, all right? I'll do the easy part for you. Then what? What would you do here? So let me ask you this, right? Forget this tau star for now. How would you get a hold of tau?
Do we just, because in the first line, we're just taking the max, so we would first just test every time point, I'm assuming. So we would,
All right, Cherry, I like that. But so, right, to what I just write down literally what Cherry says, right? Test every time point. And then I guess take the max, right? That's roughly what you're trying to say.
yeah.
Now, all right. Meet also says something very, very exciting. Okay, first let me, and so let's say this is 2A, right? 2B, take the time that S takes its max. I like this idea a lot. Because right, why not? Yeah, Sherry even likes it. But first of all, let's just go back. Okay, maybe Sherry likes it. And I guess the class likes it, right? Wonderful. Let me ask you this. If that sounds so wonderful, why don't we just go, quit this class, right? And go out there and start trading American option. We're not making much money here, you and I, right? Let's go out there, right? Find the time that the stock is max and then all trade our American option, and we're going to be rich in a year or so, right? And we all can go to Bahamas together, you and I, retiring. Is that okay? Shall we start trading American option tomorrow? Okay, being facetious aside. Yeah, I don't know about the 10 to T over 2, but exactly we don't have access to the future. So the time that S takes on its max in view of the whole path, yes, you know where it is. But you see, the whole point is this is not a stopping time. Okay, remember the whole definition of stopping time is that it's the time that by observing the history of the stock, whatever that is, right, up to that time, you know if it happens or not, right? The max exactly is not something that falls into that category because, right, by the time you observe this, right, like let me demonstrate, right? So here, this is big T, right? This is all we care about. Suppose the stock has done like that so far. Is this the max? I don't know, right? If it goes like this, sure. But if it goes like this, yes, it's the max. But if it goes like this, definitely not, right? I don't know. So yes, right? So you see this time right here, right? I don't know if the max is there or not. So it's not a stopping time. So you see exactly this saying, right, that is going to be all the stopping time is a safeguard for us not slipping in something that can predict the future into our model. Is that okay? So yeah, right. Unfortunately, that sounds like a straightforward idea, but it works in calculus, right? Where time is not a dimension, or time is not something that the flow of time is not something we try to address. But when you try to address a flow of time, then no, right? That simply is out of the question. Okay, but very good suggestion to begin with. I almost forgot that, but thank you. Yeah, I should mention that as a conceptual tool. Okay, so now maybe let's go back to Sherry's suggestion, unless someone else have some other suggestions. I like to hear all your suggestions, right? They're all great suggestions. All right, so let's see, first of all, how would one realistically carry this out? Sherry, if you can you describe a little more specifically how will you code this, or someone else? It doesn't matter.
Oh, so I would just like for each time point, I would calculate the payoff, I guess. Like I would
So
just,
let me be a bit silly here, right? And being
yeah.
pretentious, and I say I don't know anything. I say, Cherry, but there's so many time points here, right? How can I do it?
I would just divide it, like choose like n to be a big number.
Right. You would discrete time points, etc. Right? And then you do that.
Yeah.
Right. Great. That's what I want to hear. And I think that's what you suggest anyway. So first of all, you see, already the problem with that is there are a lot of time points, right, to do. But okay, the computer does the hard work. Okay, fine. Let's do it, right? But that's already a lot of painful calculation, right? But second, though, right? Suppose that we do that. Is that enough? Is that all? Is that really it? Right? That's the second question I have for you. Suppose that yes, right? And I accept that. Suppose you divide it to very fine time points, and at each time point you test it, you do this, and then you take the max. Is that all there is?
I'm not really sure because I think because it's continuous time, we might skip.
Oh, that's fine, Sherry. That's exactly
Oh.
where I can accept that because you make it really fine, then you kind of approximate, right? That's not the issue. That's fine. When you make it, the division very small, that's fine. It's just the same as when we try to differentiate, right? We just do the difference quotient. That's fine because it approximates. That's not the issue. Is there anything else that you're missing?
I might need to think about it for a bit then.
Okay, yeah. Right. So you understand what Sherry was saying, right? Sherry was saying that, just for each time points like this, I plug in, right? I do the Monte Carlo simulation, blah, blah, blah. And then, actually I simulate a path, right? For each path, I do this, and then I aggregate, right? Whatever points I get in on each of them, I compare, right? Very painful procedure, but sounds okay. Anything that is problematic with that, actually, besides the painful part? All right, let me say this, right? The problematic part of it is, unfortunately, however painful that is, it does not even cover half of the story yet. Because what Sherry was suggesting, do you realize, is deterministic time? In other words, what you're saying is, I will exercise next Monday, next Tuesday, next Wednesday, and I count the time back. The whole point, right? Even though, for example, the max is not allowed. On the other hand, right, the class of time actually is much richer than deterministic time. It allows for random time, right? As long as that random time is known, is a stopping time. In other words, right, there could be time like this. There could be the first time that the stock goes above, 105, right? The first time it crosses some barrier. That's a legit time. Now, if I were to do that, right, if I were to consider, for example, let's say tau is the first time that the stock hits, let's say 105, then what do I have to do? Then for all the path, right, like this, I have to look at the time that it crosses 105, which is different for different time. Do you agree? And then I have to evaluate those at that time, and then discount back and take expectation. Do you understand what I'm talking about? Now, how many time like that can you take? The answer is uncountably many, right? What kind of barrier are you taking? But second of all, right, even worse, this is just one kind of time, one kind of stopping time. There are other kinds of stopping time, possibly, right? How do you know that this captures all stopping time, right? Unless you can prove some statement that says all stopping time takes on this form, which I very much doubt, right? Maybe you will look at some weird stopping time like this. The first time that the stock either is above 105 or less than 100. Technically speaking, it's just a combination of two times. but still, right? So the point is, this set right here is potentially uncountable. There are too many things in there that simply listing them out and take the max is not possible even to think about, let alone coding it up. Is that okay? So I think this exactly goes back to what Meet was describing, right? Where Meet wants to do simulation and then, kind of see where the max expectation is and then compare, which is along this idea, except, right, that runs into the same issue. How do you know that you have listed out all possible times for you to consider? Because, right, when you want the max, you must have the list of the things you want to take the max off. If that list cannot be meaningfully captured, right, because there are too many of them, even with a machine, right, what are we taking the max off? Is that okay? Do you understand? So the Monte Carlo approach, naive even, cannot be described here meaningfully. Is that okay? Any question on this? So Professor Larson, I think he asked it when I will cover American option. I think he plans to describe this from a computational point of view in his computational finance class this week, I think. So if you want to see how you want to do it, then, his classes, definitely where you want to go to. I only have this to say, all right, that the topic of simulation and, computing American option, it may surprise you because this is such an old topic. I think it's still an ongoing research on how to do it efficiently. So it's a very, very, very difficult question, much more difficult than the exotic, option we consider. There is just efficiency, how you make it speed up. Here, even the question of how to do it, right, is hard. But I'll mention one thing here, just because it's so classical. The classical approach is by the idea of conditional expectation. But of course, conditional expectation here is in the sense of, simulation, not computation, all right, not formula, and is addressed in a paper by Longstaff and Short. This paper is so classic that everyone would know it. Let me tell you, it's surprising how the state of business goes. When I start, kind of working with my advisor, which by the way is like, I don't know, 12, 13 years ago, he assigned this paper for me to read. I still remember reading this paper and I didn't understand anything. But that was then, and at that time, I think this paper has already been like at least 15, 20 years old. Another 13 years, and I just talked to Professor Larson, this is still the kind of the simplest thing people can come up with. So there's some improvements, but nothing too significant away from this paper. So, like that's just how kind of difficult this problem is, maybe, right? I suspect Professor Larson will say something along this line of this paper to you in his class. I don't know, right? But it's definitely not something we can cover in our class. So we won't discuss this approach. All I ask is you appreciate, right, that it's really tough to address this kind of question, okay, in the model Black-Scholes. And again, you see why, for example, with the binomial model, right? So this is where model matters too. With the binomial model, somehow things become very nice because of discrete time, right? With discrete time, I hope you have done American option with the binomial model. With discrete time, right? It has this beautiful feature that somehow there's always a previous time step and there's a next time step. So the idea of, right, I mean, like, what do you do here? You either exercise or continue, right? And so you can walk back. However, right, tedious that is, the walking back is clearly defined, right? And then you can go back. And that actually is related to this conditional expectation I'm talking about. In the continuous time model, right, there's no next time step, right? So walking back becomes kind of a little bit, meaningless. But if you want to approximate, right, the binomial model, approximate the Black-Scholes model with binomial model, I suspect that can be done. The number of time steps becomes very large and number of branches become very large. So I'm not sure if that, is entirely attractive either. But just, the framework, right, the model somehow drives the computation. And I hope you see here that the model, right, the binomial model makes the American option quite at least easy to think about, because there's a previous time step, there's a next time step. So my decision becomes clear, right? If I don't do it now, I do it the next time step. But in the continuous time, right, there's no next time step. So the whole class of stopping time I have to consider becomes much, much more difficult to handle. Okay. So, all right. So I want to tell you that much. So the next thing I want to talk about is the martingale characterization. Of American options. So, let me just put out a kind of a blanket statement, right? The usual statement, we say, right, the discounted option price, whatever that was, right, exotic, European, whatever, right, is a martingale. It's a, P tilde martingale to be precise, a risk neutral martingale, but martingale, right, nevertheless. So tell me intuitively what is a martingale, right? So suppose that someone who doesn't know martingale, who's in the business world, right, who's intelligent, but they don't know much math and they don't want to hear much definition, like, technical definition. How will you explain martingale to them in simple language? Right? What do we mean when we say something is a martingale, right? We throw this term around all the time, right? It has technical meaning for us, but what is it really that we're trying to say? Incorrect, right? I don't know what you mean by that, but definitely incorrect, because this is very much dependent on time, or maybe something else, right? There's something that's independent of time here, but not the object itself, right? Not the object itself. There's something that does not depend on time. I think that's what you're thinking of, but this is not the martingale itself. So I think maybe along what Kashif was saying, right? First of all, constant, exactly, Kashif, right? Very good. Constant expectation is the first feature, right? In other words, right, what does it mean? Whatever that is, the object of that is a martingale, its average value should always be the same at any time. Okay, its average value will be the same at any time, right? And what does that mean, right, in our context? And why do we keep saying that these kind of guys are always a martingale? Why? Because, right, these are, notice what is this object? This is just discounted, right? This is actually just the present value, right? Isn't it? This is the present value of the future value. So basically, you're just pulling the value, future value back to the present, right? You're just pulling the future value at any time back to the present by discounting. So, but of course, this is a random quantity. So to compare it with the present, you must turn it into a constant object by taking expectation, right? Taking the average value. So, right, and of course, you see the magical equation is this, which is exactly the constant expectation, right? But again, right, I've emphasized that there's a financial meaning here that you want to keep in mind. The financial meaning is, right, when you pull the future value back to the present and compare it to the present, it's the same as the present value, right? It's the same as the present value. So in other words, right, from the point of view of any future time point, the current price, the current value of the option is equivalent to that. Why? Oh, simple answer. I can always buy the option right now, right? And keep it into the future, and I will receive the future value, period, right? So for that reason, right, any time point in the future, the equivalent price, right, to the present must be the present value. That's it. And that's why it must be a martingale, right? So that's it, the constant expectation, right, idea. I mean, of course, right, I mean, if you want it, the real deal is something like, conditional expectation, right, like this. This is the real definition. This is the general definition, but it just kind of generalized the time, right? So this is a point of view of time from time zero, right, viewing the future. This is the point of view of time from time little t, right, viewing the future, big T, right? It says the same thing, really, right? From the point of view of time little t, right, looking into the future value right there, discounting back to the time little t will have the same value, right? Why? Because if you buy at this price, in the future, you will get that price. So that's that, right? Anyway, great. So let's say this, right? So let's now revisit our American option. Which says, right, that at any time, it's going to be the max of all the classic stopping time from little t to big T of expectation, discounting back from that stopping time. Like this. All right, so one important question is, right, is the discounted value process a martingale? Is the discounted value process a martingale for American option? What do you think? Again, right, pay attention. This has implication for us in terms of the PDE, but it even has simple financial implication, right, because of the value relation like this. So is it a martingale? Is the discounted value process a martingale? Yeah, no.
My guess is that it would depend on
what?
What kind of tau we're working with.
So first of all, right, there's something here. This tau goes into the future consideration when I look at the value payoff, right? And I take the max over it. So after I take the max over it, I think the tau disappears. You see what I'm trying to say? The tau here is something like that's like, allow you to take into consideration all future scenarios. You pull it back, and then you only get the dependence on little t, right? So after I get this object, I ask if that object as a t function is a martingale. So the tau consideration, I think, is done. You know what I mean? The tau is only considered when I construct its value. Does it make sense? Yeah. So let me ask this, right? A simple question is this, and maybe that's kind of related to what Kashif was saying, right? Can this hold for American option? In other words, right, let's by the way, this can be an interview question, I think, because it has financial implication. It's not really math even, right? What am I saying here? I'm saying that I can trade the American option right now, right? Value for a future value of the American option at time t. Is this true? Think about it. In the realistic context, right? I can trade an American option right now value for a future value, right, of that same American option. Is that true? All right, let me, one key way to approach certain things is you can make it more concrete, right? Let's be realistic. Let's be simple, right? Let's say I have an American option on Google stock, right? Call whatever you want. Well, call is too easy, right? Because we only know we won't wait at that time. Let's say put or something more interesting, right? Let's say put, whatever. You can either have it now or you have it in 1 month. Are you indifferent? Are you indifferent in having the American option on Google now or in 1 month? Yeah, why not, Kashif?
I guess if you can get the same value now, you would probably get it now rather than waiting for option to expire and have it.
No, not expire, right? It will expire in a year or so, right? I mean, I'm not cheating you here. I'm not trying to say it expires and I give it to you. I say, let's make it concrete to say it expire in a year. I can either give it to you now or I give it to you in 1 month. Okay, let me draw back. Let me pull back, right? I can give you a Google stock now or Google stock in a month, right? 1 share. Well, of course, with the provision that you don't need money or anything like that, within this 1 month, you don't need cash, right? You're not desperate for cash or anything. If I give you a share, one share of Google now or in a month, do you have any preference?
So, like, what would be the value if I get it in the future, like after 1 month? It would be the
whatever that is at that time, right? I give you 1 share. By the way, right? A share is just a piece of paper.
Yeah.
Agree? So if I give you a share of Google now or a share of Google in the future, do you have any preference?
I mean, from my perspective, I would, it's kind of a tricky question. So financially speaking, I mean, I would be indifferent in having it today or tomorrow if it's the same asset that I'm getting.
Yeah.
But if it is like, if I'm feeling like there would be a kind of a price hike or price raise in a short time frame and then goes back to what it is now, then like
No,
it's
I know, right? But exactly, you see, by polling all this, short price hike, that kind of thing, you know what you're dealing with. You're no longer risk neutral.
Yeah.
Right? But if you're risk neutral, right, meaning that, or let's just, maybe, I'm not sure gold will make any difference. But if I give you 1 ounce of gold now, or I give you 1 ounce of gold in a month, and suppose you're oblivious to market movement, right? I mean, you don't know about price hike. And by the way, maybe you don't plan to buy or sell, right? Then I hope the answer is you're indifferent, right? Whether you receive it now or let's say tomorrow.
Yeah.
Right. By the way, right, this exactly doesn't apply to cash. If I give you $100 now, or I give you $100, a month from now, right? Then $100 now is preferred, right? Because of time value of money. Agree?
Yeah.
But of course, if I give you a saving account now and a saving account in the future worth, whatever the denomination, then you should be different because a saving account will accumulate that saving for you, right? Anyway, so that's exactly what we're talking about is the martingale feature there, right? The value is constant. Okay, now when it comes to American option, if I give you an American option on Google now, and I give you American option on the future, Google, right? 1 month, are you indifferent?
No, because I would have more probability of having profit if I get it early.
Can you elaborate?
So I would have like more time where I can have my stopping time available for me to execute my trade.
Absolutely, I think that's exactly it, right? The American option exactly has that extra feature that makes it different for you to trade from here to here. Because, right, what if the optimal exercise time is sometime in between 0 and little t? Then by trading in like this, right? Because you see, at this time, the only option left for you to exercise is from time little t to time big T, right? So in other words, the answer here is no, right? Because the optimal time, right, tau star for V0 may be in 0 to t, right? Or put it in a different way, right? So V0, right, is the soup from 0 to t, right? Like this. Which set of time is bigger? Which has more option? Clearly this, right? This has more option. So even though, notice, right? If you cover all this thing, sorry, I'm not covering, I'm only covering on my iPad. If you cover this, right? Then from the point of view of the payoff, that's indifferent. Sorry, this is tau, right? This is tau. And by the way, sorry, I'm messing up here. There's no 0, right? But if you cover the soup, then from the point of view of discounting, right, because it's on the stock, you should be indifferent. But you have more option here, okay? You have more option here. So in that sense, this is not equal. But which direction you think it points? Is there a direction that we can say like this or that?
I think greater than.
Or equal to, right? I
Oh,
mean,
yeah,
it could
sorry.
be, yeah, exactly. Very good. So when things point in this direction, it's definitely not a martingale, but is there another term that we can say? I think you might have learned from Professor Larson. What do we say here? Do you know?
I always get it mixed up, but I know there's like super and sub martingale. I think this one is super, but
Yeah, I guess
I
maybe
always get it flipped.
you're right. I think maybe I'm not sure this is a good device to remember, but maybe super is not so super, Super actually is bad because, I mean, it's not really bad, but like decreasing, right? Super is decreasing. So if you remember super is not so super, I don't know if that helps. But yeah, exactly. So the discounted option price, right, is a super martingale. Okay. So that is the key feature of American option, right? And that's going to be a break from altruition, right? That usually we see things as martingale. Why? Because there's no kind of time consideration like that. There's no action in between that you can make, right? So you don't lose out on anything, right? If you are risk neutral, right? If you like the talk I was having with Kashif, if you just look at one share by itself, you're indifferent, okay? But because of, right, the longer you wait, the less option you have available to optimize. So that hurts in that sense. So in other words, right, the longer you wait, the more your value tends to go down, right? Doesn't have to, but right, it tends to. All right. So I will not elaborate more on this, but I would say, you know, for more technical proof, see the notes. So in other words, if you want to see like, you know, the calculation done out, I prefer to just, you know, stop at the intuitive explanation, unless it's not clear, you want to see more. Is this okay, or anyone wants to me to elaborate on this? The key, right? The key relation exactly is just the comparison between this and this, right? You have much more option here to optimize. You have less option here, and of course, right? You push it to the limit. At time big T, you have no option, right? You have to exercise. That's it. Okay. For more technical details, I guess. The second thing I want to tell you is this, right? That so on optimal, right, stopping time. So on tau star, okay? So first of all, I was telling you that, right? This guy right here is not a martingale, right? It's a super martingale in general. And then second, I want to address this tau star business. Okay. Now, first of all, let me ask a very silly question. Suppose tau, at the time tau is where you exercise, right? So what's V tau star? What's the value of the option at tau star? What's V tau star? It should be. Yeah, right. But if we don't talk about put, right? Yes, Kashif, very good. But in general, right, it's just whatever payoff function we're looking at, tau star, right? Very good. Yeah. Okay. So, right. So let's see this. Let's just contemplate this a little bit. So here's 0, right? Here's T. Let's say tau star is somewhere in between. Doesn't have to, right? But just let's just kind of suppose that's the case for this particular instance. So our stock does whatever it does. Whoops. Right. And like this. Okay. So obviously you have this too. V0 because of this. V0 is this. Because that's what we have. Right. But on the other hand, right, we say that this is a super martingale. Right, is a super martingale. So how does that connect with this observation? With just the notion of tau star, right? In other words, right, suppose this is where if there's such a time, right, I exercise and I get the value like this. But if my value tends to decrease, right, like this, then why do I even, right, have an optimal exercise time? You understand what I'm trying to say, right? If something is a super martingale, right, don't you just want to exercise it right away? So what makes this tau star non-trivial? In other words, why it is not 0, for example? Anything that might happen here that, you know, that could, I don't know, right? Because a super martingale should make you super suspicious, because no one would want to hold on to anything that's decreasing in value in general, right? Do you agree? If someone right, I mean, yeah, maybe let's make it very financially very easy, right? Anytime any day that goes by, you have less and less decision to make, right? Any day that goes by, you have less and less decision available to you. So from that naive consideration, why would you want to even wait to begin with? Right? I mean, it's like someone who says like the very first day is the best day of their life because they have all the options available. Any suggestion? So let me say this, right? It turns out, and it should be the case, that VT must be a martingale. I'm sorry, someone say something. So VT must be a martingale on 0 to tau star. So, right, it's a super martingale in general, right? But up to that time when you optimally exercise, it does not lose value. So that you can just pull, right, whatever the value back to the present, right? So up to that optimal exercise time, right, you're indifferent whether you hold a stock now or until that time. Does that make sense? Obviously, because, right, that's the whole definition of, like, you know, exercise time anyway, optimal exercise time, right? It's a time that you know, exercise. Before that, you don't. So of course, right, you're indifferent for holding the stock, right? If you're not indifferent, then you will already exercise at the beginning. But by the way, right, unless you're suspicious, the super martingale does allow, right? A martingale is actually a super martingale because equality, right? The definition is greater than or equal to. So equality is fine. So a martingale is a super martingale, right? So this is not quite correct, but what happens is this, right? It's the martingale up to that time, and then it may start to decrease in value after that, right? If you miss that window, if you miss that first window, right, to exercise, then, right, you lose value. But up to that first window, you don't lose value. Oh, sorry, right, I forgot the discounting. Any question on this? Okay. So another observation. This one is quite trivial, right? We say this. The value, right, of the option is always bigger than its intrinsic value. Again, if we use that term, right, it's always bigger than its exercise value, right? The value of the option is always at least not worse than its exercise value because you always have this available. All right. So I wonder, this might be a bit of a stretch, but we have this, and we have this, and we have that. It's a martingale up to that time. Can you, I don't know, it's a stretch, but I'd like you to see. Putting this together, can you make a guess on what this guy is? What is this mysterious tau star? So the discounted option price must be a martingale from here to here. The option always is higher than this, right? Or is no less than that. And then, right, at the exercise time, then the value of the option is equal to this intrinsic value. What is this mysterious tau star? No, because if tau star equal to 0, then that means that we always exercise, right? And that we were not going to be here discussing the American option. Right? Tau star equal to 0 means you immediately exercise every time you have the American option. That can't be right, right? Because European option, American call, right, asks you to wait. So no, that's not true. Yeah, right. Actually, with the American call, what is tau star again? With American call option, what's tau star? Correct. So can you guess what tau star? And by the way, right, why is this the case? I'll give you a big hint here, I hope. Because, right, V, right, American call at any time t will always be bigger than st minus k plus, right? Is that right here? What we just talked about. And of course, right, at time t, V American call at big T is equal to st minus k plus. So can you guess what tau star is in general?
Tau star would be like something akin to a stopping time.
Sure, but what kind of stopping time is it? Can you characterize it?
One that would be in between lowercase t and uppercase t.
So I'm asking is this, right? When you say a stopping time, you should describe a rule for it. For example, the first time that a stop hits 150, that's a stopping time, right? First time that the stock goes below 80, that's a stopping time. I mean, without describing such rule, right, then the stopping time is very vague. Does that make sense?
Yeah, I see.
All right, maybe let me just say this here. Tau star is the first time that, so let me do this, tau star of t, okay? Is the first time that the value of the option is equal to the exercise value. So let me explain a little bit here what this notation is. This is the stopping time for VT. So in other words, if you already start at time t, then this is the stopping time. But so what it means is if you start at time 0, then tau star, right, or tau star at 0 is just the first time that your value of the option equal to the exercise value. Okay, what that means is this. You start here, right? You have the option value, which is always no less than exercise value. You wait and wait and wait and wait until the first time that your option value is equal to this. And that's the time when you exercise. Is that okay? The reason why we write this, right, is because the story can happen at time little t. In other words, right, you can start the option now at time little t, right? And then so that you wait and wait and wait right here until the first time that your option is equal to the exercise value. Is that okay? Right? And that would be consistent with all these things. So in other words, right, your option price is always no less, right, than the exercise value. And in fact, before time tau star, it should be bigger. Okay. At the first time that the option price equals to the exercise value, then you exercise. Right? And if you do this, then the whole process will be a martingale up to that time. By the way, right, look at this in the American call option. In American call option, you see, the option price is always bigger than the exercise value. At the optimal exercise time, right, the optimal exercise time, you see, this is the first time that this is equal to this. because right before that is always bigger. Does that make sense? So the rule for the optimal stopping time on general for any option, for American option is this: you wait and wait and wait until the value option is equal to the intrinsic value, the exercise value, and then you exercise. That's yes, optimal system. Okay, so let me ask you this, right? Does this help the simulation? In other words, right, I asked you about the Monte Carlo simulation. So now you know what tau star is, right? It's not some mysterious object. Now, can we go back and do the simulation now? Right? Can we do better now that we know what tau star is? So tau star, right, will be the first time that the value is equal to this. Don't think so, right? We know tau star, so we should be able to simulate it better. Anyone else have any other thoughts? Well, unfortunately, the answer is no, it doesn't help. So yeah, so Don, right? I mean, that unfortunately doesn't help. Why? Why is, right here is the object you're looking for, right? The whole point here is to find V0, right? So V0 is the unknown object. When you say that it's the first time that the value process equals to the payoff, right? So by the way, this is known. By simulating the path of this, you know this. But exactly this is the unknown object to begin with, right? So by saying that this is the first time the value process is equal to the payoff function, but this is unknown, that defeats the purpose. I mean, I guess tau star does, Don, right? Tau star does define V0 in some way, but that way is very convoluted because it involves VT in the future. You see, that's the, I don't know, that's really the difficulty of this question, right? It's just the way the American option constructed, you see. But tau star itself, by the way, right? I think the way to compare this is with the barrier option, right? The barrier option says if the stock price hits some barrier, you're out of the money, right? You're zero. That is actually very simple because if I follow the stock, right, I know exactly where I'm out of I'm striked out. Here, even if I follow the stock, I do not know what the valid option is. So this definition, okay, it's a good definition. Okay, it is a very good definition, except it doesn't give you anything unless you already know what VT is in some way. So of course, mathematics is such that when you bootstrap things, you know this and you know this, you can know something more. But for now, I just want to draw your attention to the fact that this does not give you anything extra, right? It somehow is very mysterious that it refers back to the value process itself, right? So unless you know the value process, this is right, not very useful. Okay. Any question? All right. So now that's the two things. So now let's go to the analytical solution or closed form solution. In the perpetual put. Okay. So first of all, right, perpetual means T equals to infinity. There's no expiration. All right. I don't know if there's any real life product that's perpetual. I mean, I do know there's some perpetual, contract or something like copyright, whatever, I don't know, right? But in terms of option itself, I'm not sure there's a perpetual option. But at least, I mean, you can see that if T is far enough, 10 years, I don't know if there's any 10-year option, but if there's some T far enough, we can, for some, practical purpose, think that it's infinity, all right? But what's the effect here? So first of all, right, why only perpetual put? Right, why not? So sorry, right, perpetual American put, that's what I mean, right? Because I mean, if it's European, then because T goes infinity, that means you never exercise, that's meaningless, right? So why not perpetual American call? Okay, why not perpetual American call? And I hope, right, the answer is clear. And that's exactly what Mead was mentioning, at the beginning, right? Suppose there's no T, right? And this is your K, right? Then exactly you see one point, the point is that our model, our stock model, right? The Black-Scholes model is such that the stock price will never be zero, right? Because it's exponential of something. So in other words, right, never bankruptcy, never bankrupt. Bankruptcy never happens, which by the way, right, is a unrealistic assumption too, because company goes bankrupt all the time, right? But I mean, suppose that somehow you have a hypothetical company that never goes bankrupt, right? By the way, I don't think there's anything like that in history even. If you have a perpetual call option on a company that never goes bankrupt, right? Then the point is what? Just to wait and wait and wait for a stock to goes up, right? Because you never want to exercise, right? The more you wait, the more it goes up. Yes, and exactly what Mead was saying, right? There's no upper bound on the payoff. And if it doesn't go bankrupt, then there's no early exercise, right? On the other hand, right, of course, I would say this. The question of a perpetual American call may be interesting if you consider a model that allows for bankruptcy, right? Because suppose, right, that a company can go bankrupt, then at any time point, right, you may have to worry about the future potential that your option is worthless because the company goes bankrupt. So in that sense, right, you may want to exercise early. So even if it's perpetual, you don't want to wait forever, right? Because the longer you wait, the more likely, like, the company will go bankrupt. The Black-Scholes model does not allow for bankruptcy. So the question of perpetual American call is meaningless. Is that okay? But perpetual put actually is meaningful. Why? Because, with the put option, right, the time value of money work against you, like with the minus R, right? I was saying somewhere here, right here. The time value of money work against you. So even if I give you the whole, future, right, until the universe ends to exercise, you may not still want to wait that, because the longer you wait, the more it hurts, right, in terms of losing time value of money. So maybe I would just say, like, why not a perpetual call because of this, right? But perpetual put makes sense. All right. So what is the advantage of the perpetual put? Consider a perpetual option in terms of, like, just playing around with the math. In a perpetual put option, right? Remember V, right, usually is a function of T and ST, right? If you have perpetual option, you don't have the time dimension. You only have the spatial dimension. So in other words, right, at any time, right, the value of the perpetual put remember, perpetual means the whole future is up to you, right? You have the whole future ahead of you. There's no right time window that the time to expiration is decreasing. No, right? Time to expiration is always the same, which is infinity, right? Because of that reason, right? Any time point looks the same to you, right? Any time point looks the same to you, right? There's no big T minus small t waiting for you like that, right? There's no time to expiration. So therefore, the only dependence left is on the stock. Is that okay? So that simplifies the problem a lot, because then you don't have to worry about how the time depends. Okay. So I would say just one more thing, that this also is because the Black-Scholes model is time homogeneous, but won't worry about that for now. Meaning the stock price behaves the same, doesn't matter where you are in terms of time. All right, so the question is, how do we categorize V of X? Okay. And I'll say this, right? We categorize it in 3 ways. V of X satisfies the following. The first one should not surprise anyone. Is always, right? This is the value of the option, is always higher than the payoff function, right? Or no less than the payoff function. The second one may be a bit surprising. I don't know. Minus RV plus V sub X Rx plus 1/2 V sub XX sigma square X square, right? And 0. You recognize what this is, right? This is your good old Black-Scholes PDE, except there's no T dimension, because, right, the time goes away in perpetual, right? In perpetual option. So there's no VT. Correct. It should not be little t, right? It should be big T, but anyway, yeah. So, but anyway, what is it here? Equal to 0? What's your guess? Equal to 0? What are we doing here?
I don't think it's equal to, because we have the fact that it's a super martingale. So
Great. So what sign?
I'm guessing greater than or equal to, but I haven't thought about it yet.
Remember, right? This is the DT term, right? This is basically the DT term, right?
Yeah.
And super means going down.
Okay.
If it goes down, then what makes it go down? Less, right? Because dt is a change in time. As time goes on, you must go down, right? In order for that to be a super martingale. Is that okay? Or I think you will see that people do it like this. Is that okay? Now, but that's not it yet, right? So this is the super martingale, like what Don said, what Sherry said, right? Super martingale categorization. One more thing, right, is this. We can say this. This is going to be equal to 0 on this. And 0. Okay. So on the last part, does anyone know why this is true?
Wait, sorry, can I ask a question?
Sure.
So is it when we say it's equal to 0, is this like talking about all the time points up to the stopping time?
That's exactly is it. This is exactly because it's a martingale up to the first time cow star. That's exactly that characterization, right? Because you see here, you are still not there yet. Yeah, go ahead. Okay, you're good, right? So by the way, right, this together is something called a barrier equation. Or sorry, obstacle equation. Okay, why obstacle? It's basically because, you know, at the heart of it, it's like your good old ODE, right? For example, good old ODE PD, except that you see that it only holds on certain domain. It only holds on a certain domain. And then the value of the function itself, the solution itself is required to be greater than that. Okay, so it's called the obstacle equation. Now, it turns out somehow by a stroke of luck or by analysis, we have explicit solution here. Okay, so I know that time is running out. So I will say this, right? See notes and homework. So in other words, I think it's just some equation, all right? It's not something very amazingly illuminating. So I ask you to play around with this, the solution to this, and kind of check that it's consistent with all the things we've been doing so far with, guess what, simulation, right? And with, you know, calculation on homework and in the review session. The point is this though, right? Once we have this solution, then we can pretend that we don't know it. And then we just use it to verify all the properties we have before. The hard thing is somehow to solve this equation in general, all right? And it will be hard if we don't have perpetual option. Okay, and we'll discuss more next time. But for now, let's stop here and I'll let you play with this at home. All right, so thank you for participating, guys. And if you have any question, I'll answer. If not, then I'll see you next week, okay?
All right, thank you, Professor.
Thank you, Don.
Oh, I just wanted to ask, like, approximately, do you have a time set for when our final exam would be?
I do. I thank you for reminding. I think Anna did send me a schedule. I forgot to tell you guys. So I will put that on an announcement right after this. I have it. I just forgot to put it up. So I will, right? I think sometime in May, I will put it up. All right.
Okay, perfect. Thank you so much.
Sure.